Thank you. I will begin. Dear Heavenly Father, we thank you for this day, and we thank you that the CFAWs are not here yet. Help us to enjoy this time we have together, this more academic time before they descend upon us. Help us to enjoy this time, and help us to learn math today together. Amen. All right. We just a few short hours before the hordes descend upon us, as you know. So today we're doing power series solutions. To ODEs, of course. Now, so I ask you a question. What is a function? Do you guys have a good answer to that? What is a function? Has to be 1 to... No, it doesn't have to be 1 to 1. Like f of x equals x squared. It's not 1 to 1, but still a function. What's that? It's going to hear you. It's continuous. It doesn't have to be continuous. It could have absolute value. Like the unit step function, still a function. It's discontinuous. These are all nice properties for functions to have. Things you guys are telling me. But how about this? Some of you have taken Dr. Sperano's Calculus 1. I'm assuming there must exist. Anybody? Show of hands. Who took Dr. Sperano's Calculus 1 in here? So you guys remember from test 1, question 1. What's a function? Oh, yeah.
For every element in the domain.
It's 5.
For every element in the domain.
It's 5 math classes ago. So our modern set theoretic explanation is it's a single valued assignment, right, of each point in the domain to some point in the codomain, something like that. And you could rephrase it in terms of set theory if you like, but you see, back in the time of Lagrange, like, around the Revolutionary War or so, that definition wasn't really out there. And so back then, we defined functions by formulas. So it's more like what you do in pre-calculus. A function was something, the distinction between function and expression was blurred at that point in time. It took mathematicians a while to really come up with the modern definition of function, which you guys have now forgotten, which is fine. But it's okay. But what Lagrange said is something like this. He said a function, he said consider a function. Something like y is equal to a0 plus a1x plus a2x squared plus a3x cubed plus ... I mean, if you look at Lagrange's book on calculus, circa like 1780, he starts the book by saying, imagine a function like this. So to Lagrange, this was sort of like the penultimate, most general way you could say what a function was to say it was a power series. All right. So what I'm trying to get at here is if you consider expressions of this kind of form, there is tremendous flexibility in assuming your function has this sort of form. This is a power series centered where? Centered at 0, right? Let me remind you, definition. If we have f of x, bless you, sum n equals 0 to infinity of an minus n times x minus x naught to the n. This is a power series. It's centered at x naught, right? And it has coefficients a sub naught, a sub 1, a sub 2, ... all right? Now, we're going to deal, for the most part, with real power series. So this x naught is a real number, and these guys are also real numbers, okay? So in the plus ... notation, this looks like a sub 0 plus a sub 1 times x minus x naught plus a sub 2 x minus x naught squared plus ... So if a function has a formula like this, it's said to be a power series, right? The domain for such a function is what? We call it what? Usually we call it the IOC, right? The interval of convergence. And that makes sense because the domain is always an interval. Well, that's not entirely honest. I mean, the interval of convergence has three generic forms, right? Do you remember what it was? It could be just the center, right? It could be the whole reals, right? Or the other possibility was it's something like x naught minus r, x naught plus r. But remember, there's interesting stuff that happens. You might exclude both endpoints. You might include both endpoints. You might exclude the left and include the right. You might include the left and exclude the right. Those are your 4 flavor choices. Now, these 3 different cases, the distinction in them is the radius. The radius of convergence here, 0. The radius of convergence here is what? What's the radius of convergence if it's the whole reals? It's what? Did you say? Did I hear infinity? I want to hear infinity. I'm gonna pretend I heard infinity. Now the radius of convergence here. Is that what you said? Yeah. Oh, I'm sorry. I couldn't get it out. Okay. Oh, okay. Okay. I'll accept it. The last one here, the radius of convergence is just r, whatever that is. All right? So that's what we're looking at. That's what we expect. We know that when we're working with power series that this is sort of the terms and conditions. If you have a power series, it's either going to make sense at a point, which is very boring. It's going to make sense on the whole reals, or it's going to make sense on some open interval, closed interval, or half open, half closed interval. Yeah, right. And it turns out that if we assume that our solution to a differential equations has the form of a power series, this is a very robust guess. It covers all kinds of differential equations, many, many things. Everything we've already done, and much more, actually. Well, that's not fair. The Laplace Transform technique, it picks up the pieces. Like, this is not a good technique for discontinuities, honestly. So Laplace Transforms still have their day in the sun, so to speak, because these don't do well with discontinuities. That's true. So let's look at, let me just, a quick reminder. What are some power series we know? We know power series expansions for sine x, cosine x, sinh x, cos x, e to the x, things of the form 1 over 1 minus r, inverse tangent x, natural log of 1 plus x, etc. We can find power series for all of these. And we learned how to do that in 132, right? Now, rather than giving you a catalog of those results again, I'm just going to start working some examples, and we'll come across the results as we go, all right? So let's look at example 1. Let's solve y prime prime plus xy equal e to the x to order 2. Okay? Oh, there's one other general thing I should say before I get in. There's just one thing. It's bad for me not to say this. What was the big theorem that was in all this? One big theorem that I should at least take a second to remind you is, convergent divergence, we don't care about that. You like that? It's music to your ears. But we do care, and we care deeply about this, is that f of x is equal to the sum n equals 0 to infinity of the nth derivative at x naught over n factorial times x minus x naught to the n. Now, it's not so much that I'm endorsing that as a way to find power series. In fact, that's usually a bad way. But this interpretation that the meaning of the coefficients is tied to the derivatives, that's very important to us. So in particular, the first few terms, you got f of x naught, right, plus f prime of x naught times x minus x naught plus 1/2 f prime prime of x naught times x minus x naught squared. All right, that, especially even the last thing I wrote, is very important to us. Let me tweak my first example just a little bit so we kind of roll that idea into it. So let's add a little bit more structure here. Let's look for the solution. Let's assume that y of 0 is 1 and y prime of 0 is 2. And let's up our game a little bit. Let's look for order 3 just to make sure it's interesting. Okay. We're going to solve that. And we're going to solve, let me finish the thought here. Use power series technique, okay? So the basic power series technique is to assume the solution is a power series. In other words, to assume y is equal to a0 plus a1x plus a2x squared plus a3x cubed plus ... Right? Where a0, a1, a2, a3 are unknown but soon to be known constants. All right? Then we do what we do in every single part of this course. After we make our guess, we stick it into the differential equation and use the variability of our guess to make it work. What's the variability of our guess here? Infinitely many unknown constants, right? It's like variation of parameters, except instead of having a couple of them, you have infinitely many. Now, there's something we can do here without further work, though. Step number 1, because we know calculus 2, and we understand the connection between values of the function and values of the derivative of the function and the power series, you can immediately tell me what a sub 0 and a sub 1 are. What are they? 1 and 2, right? So that's 1 plus 2x, and then stuff I don't know. a2x squared plus a3x cubed, and so forth. Right? But the 1 and the 2, those come for free because I'm given initial conditions here. Okay. And then I differentiate. I get 2 plus 2a2x squared, x rather, plus 3a3x squared, plus ... How do you differentiate a power series? Term by term, right? I mean, that's the beauty of power series, is it essentially converts problems into polynomial problems, right? I mean, polynomial problems are good problems to have. They're harmless. 6a3x. All right, now I have done the necessary calculus. I can plug it in to the differential equation. Okay, so let's do that. So we've got y prime prime plus xy equals to e to the x. Okay, so y prime prime is 2a2 plus 6a3x plus stuff. I believe if I just look at this to order 2, I'll be able to get enough equations. We could see if I'm right or wrong. So I'm just going to keep terms up to order x in here and see if that's enough, if I can get away with it. And then plus x times y. What was y? Y is 1 plus 2x plus, a2x squared. Now, again, I don't need to actually put that last term I put down there. I didn't really need to put down. I'm just putting it there so you can see what's there. And then this e to the x. What is e to the x as a power series? So you guys, I think this actually came up the other day, but this is 1 plus x plus 1/2 x squared plus ... right? And so that's what I put over here. 1 plus x plus 1/2 x squared plus dot 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 IU. Now I have two series are equal. Two series can only be equal if they're equal order by order. So I can look at the constant terms matching, the coefficient of the x terms matching the coefficients of the x squared terms and so forth and so on up the chain. We'll start with the constant terms. Constant terms, what we got here? We got 2a2. Is there any constant term in this here? No. I mean, there's an x multiplying everything. Can't get rid of it. No constants in there. On the other side, we've got 1. Hey, look at that. a2 is equal to 1/2. If I had not erased order 2 and made it order 3, we'd already be done. Right? But I said order 3, so we got to keep going. What are the coefficients of x here? I've got 6a3 from that, right? And then I've got x times 1. So that's it. For the left-hand side, 6a3 plus 1. Right? And that's going to be equal to what? Yeah, there's a coefficient of 1 over there. So therefore, 6a3 is equal to 0. So a3 is in fact 0. And that's all I need to get to order 3. Solution is y is equal to 1 plus 2x plus 1/2 x squared plus dot 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 dot. That's it to order 3. We could invent a notation to express that the plus dot 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 contains things of order 4 and higher, but I don't traditionally do that. Yeah.
Write it as 0x.
Yeah. If you've shown this, then I know what you did. So, but yeah. I mean, maybe it would be good to say plus order x to the 4th or something, like big O x to the 4th. But I don't traditionally do that, and you know, so I'll let you guys get away with plus dot dot dot. Yeah. All right. So there you go. I mean, the idea is simple enough, right? We just assume that the solution's a power series and work it out. Question?
No, I was just saying,
Oh.
I really like how that worked out.
Yes, sir.
So, if you're assuming it's a power series,
Uh-huh.
is there a chance that it's not a power series?
There is a chance that the differential equation does not allow a power series solution, right?
So, would we run into that?
We will. That's next lecture. That is where the Frobenius method comes into play. There are also things past the Frobenius method which we won't learn how to solve. So we don't learn how to solve absolutely all things that are known here. But a good chunk of whatever comes up in applications we'll solve. So, example 2, if I wanted to solve, say, y prime plus, let's say, the sine of x times y equals to 0 to, let's say, order 3. This time I won't give us initial conditions, okay? So let's suppose we've got y is equal to a0 plus a1x plus a2x squared plus a3x cubed. So I'll calculate y prime. Actually, if you don't mind, I'm going to get straight to it. Y prime plus sine of x, y equals to 0. So that gives me a1 plus 2a2x plus 3a3x squared plus dot 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 dot, this thing. And then what's the power series for sine? Well, power series for sine is x minus 1/6 x cubed plus dot 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 dot. And then y is a0 plus a1x plus a2x squared plus, dot 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 equal to 0. Now, you can multiply that out, but I don't think it really accomplishes much anything to actually multiply that out. For me, the process of multiplying that out and writing out the multiplication tends to introduce errors. For me, personally, it's much easier at this stage in the game to think about multiplying it out order by order and collect results. So like this is enough. I've got everything as a power series. I can easily deduce from this expression what is going on order by order on the left-hand side. For example, the constant terms. What do I got? I've got A1. Anything else? No, because I got at least an x here, right? So that's it, A1 equal to 0. Well, that was not bad. It's apparently A1, 0. How about the x terms? I've got 2A2. X times A0 gives me A naught. A sub 0. Anything else here? No, yeah, because I get x cubed times stuff, that's too big. A sub 1 times x, well, that's at least an x squared, that's too big, that's it. So I get 2A2 plus A naught equals to 0. Right? What does that mean? Well, this means that the fates of A naught and A2 are linked. A2 is equal to minus A sub 0 over 2. So as a general principle, try to write higher coefficients in terms of lower coefficients whenever possible. That's what I did. I solved for the higher coefficient, A sub 2, in terms of the lower coefficient, A sub naught. Right. X squared, what do we got? 3A3, right? Now, minus 1/6 A0, very good. Ah, plus A2, very good. Ah, plus A1. The A2 does not get to play, does it? Because it doesn't, yeah. That doesn't produce an x squared in the multiplication. It produces at least an x cubed or an x to the 4.
How does A not get to 1/6 because it's cuber?
Schnikes. Learned who my friends are. Let's see here. What do we say? Just plus A1, eh? All right. Is that it? That's the only way you get x squared is the x times the A1 term. Yeah, yeah. And that equals to 0. Okay. So that tells me what? That tells me that A3 is equal to minus A1 over 3, right? Also known as 0. This is funny. So the order 3 term is 0 again here. So up to order 3 is actually up to order 2, non-trivially. I mean, like, the order 3 term is 0, so it's kind of doesn't, in some sense, I mean, this doesn't look, you know, I kind of like Mr. On's suggestion that we write 0 times x cubed plus dot, 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 dot. That's kind of a nice, quick way of expressing, hey, there's 0 on the x cubed term, you know, but I don't see that in books much or anything like that, though, so I don't know. I admit, it's starting to bother me. I need to come up with a systematic notation here. All right, y equals to, where are we? A sub 0 plus A1x plus A sub 2x squared plus A sub 3x cubed plus dot, 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 dot. Now, that's actually, we have learned what? We've learned that A1 is 0. We've learned that A sub 3 is 0. And we've learned that A sub naught plus what? Well, minus, rather, A sub naught over 2x squared is it, right? So we can rewrite that. That's A sub naught times 1 minus 1/2 x squared. plus stuff. And there you go. That's the solution to order 3. Is it surprising that there's a variable in the solution? Right. So without initial condition, we expect a parameter in the solution.
Is the last step necessary? Can we stop at a sub naught plus minus a sub naught over 0?
The last step is expected, yeah. Yeah. Because now we can see what the function is, right? We can see that y1 equals to 1 minus 1/2 x squared, right, is a solution. If you strip off the constant, you can see that that plus dot 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 is the solution here. All right, so I wanted to start with some of these kind of, just find the first few couple terms kind of examples, because otherwise I think you might get lost in what I'm about to do. So often I ask you for more than just the first couple terms. I'll ask you for the complete power series solution. All right? So to find the complete series solution, we have to use the sigma notation. So let's do a warm-up with that. Let's solve dy dx equal to x cubed. What have I not done yet? Inverse tangent of x. All right. Now here, I need to remind you a little inside baseball, so to speak, calculus 2. Here's a little calculus 2 refresher for you. If you let g of x equal to inverse tangent of x, that means that dg dx is what? It's 1 over 1 plus x squared. That, by geometric series, is the sum, n equals 0 to infinity, minus 1 to the n, x to the 2n. Then, if we integrate term by term, we get the sum minus 1 to the n over 2n plus 1, n equals 0 to infinity, x to the 2n plus 1, a constant plus that. But that constant has to be 0. G of 0 is inverse tangent of 0 is that constant. So that implies that the inverse tangent of x is in fact equal to the sum n equals 0 to infinity minus 1 to the n over 2n plus 1 x to the 2n plus 1. So there you go. That is the power series centered at 0 for inverse tangent. I happen to need that to do this problem. All right, so continuing example 3, we're trying to solve dy dx equals to x cubed inverse tangent of x. So how would you do that? I mean, my suggestion would be integrate, right? If we integrate both sides, we get y is equal to the integral of x cubed inverse tangent of x dx. How do you do such an integral? Well, you might actually be successful with some sort of traditional technique, but here I want us to use power series, okay? I mean, I could easily rain on a parade and make it so that it's impossible with traditional techniques. Here, let me change that 3 to a 33, just to drive home the point. Now you definitely don't want to use traditional techniques. There you go. Okay. So the point is, I can convert the integrand to a power series. It's the sum, n equals 0 to infinity, minus 1 to the n, over 2n plus 1, x to the 2n plus, see, I take this, but I have to multiply by x to the 33, so I get 2n plus what? See, because x to the 2n plus 1 times x to the 33 is x to the 2n plus 34. How do you integrate a power series? Term by term. So we get constant plus the sum, n equals 0 to infinity, minus 1 to the n, over 2n plus 1, parentheses, times 2n plus 35, because when we integrate, we add 1, right? X to the 2n plus 35. There you go. That's a solution to this differential equation. Power series solution, of course. And this time we added the constant like you wanted. Right? You notice that the constant doesn't always appear additively. Sometimes it appears multiplicatively, like over here. All right. So this was not the first few terms, right? This was all the terms. Can I erase? I want to start here again. Okay. By the way, this thing I just did right here is what I collectively refer to as geometric series technique, which is creatively using the geometric series to derive a power series you're interested in. Example 4. Let's work on solve y prime prime plus x squared y equals to 0. Now, this is unpleasant if we go back. I mean, we don't have a method for this, right? I mean, you could try to Laplace transform it. What would happen? What happens if you Laplace transform this? By the way, try the Laplace transform. What happens? This becomes s squared big Y. Let's assume that we're looking for initial conditions 0. Well, fine. Initial conditions minus what? Minus s y of 0 minus y prime of 0, right? Great. Whatever. And what's the Laplace transform of this? Do you guys remember how Laplace transforms work? We had x equals to t, right? But what was... That's the second derivative, right? The second derivative with respect to s, dds squared of y of s, times minus 1 to the 2, which is just 1. So this is what Laplace transforms does for you on this problem. Isn't that kind of perverse? It's almost like the Laplace transform is the differential equation again, isn't it? See that? I mean, in the S domain, it's essentially s squared y plus y prime prime equal to 0, ignoring the stuff in the middle, which is exactly what we started with. Yeah. We didn't look at any problems. The problems we looked at with Laplace, they always were algebraic after we took the transform, right? But if you have multiplication by time, that becomes differentiation in the S domain. Okay, so this is Laplace transform is not the way to go. Let's try the series technique, see how it goes. So this one we're going to have to use a summation notation for. This is the sum, n equals 0 to infinity, of a sub n, x to the n, all right? So y prime is the sum, n equals 1 to infinity, of n, a sub n, x to the n minus 1. And y prime prime is the sum, n equals 2 to infinity, of n times n minus 1, a sub n x to the n minus 2. You see why I drop off the 0th term? Because when you differentiate, the constant goes away, right? And when you differentiate the second time, the constant and the linear term is gone. So, I mean, you could leave these sums starting at 0 in both cases. It wouldn't be wrong. It would just be you have got 2 zeros at the start, right? So I might as well make it 2 because that's honest. It's not dishonest to put it 0. It's just, you know. All right. So, great. Now we have to look at, do it right here, y prime prime plus x squared y equals to 0. So what is that? That is the sum, n equals 2 to infinity, n times n minus 1, a sub n, x to the n minus 2, plus the sum, n equals 0 to infinity, a sub n, x to the what? If you can imagine what happens when we take x squared and multiply it by y. We get a sub n, x to the not n, but n plus 2. Very good. What's that? Again, so if we look at this expression right here, right? If we multiply this by x squared, that puts an x squared here, right? And then you bring that in, x to the n times x squared is x to the n plus 2. That make sense? Okay. Now, in order to add two series, they have to have matching formats, so to speak. I mean, they have to have matching powers. n minus 2, n plus 2, these do not match, right? And if you think about where they start, there's a disparity here, right? This one has what? This has constants. It has constant terms. It's got x squared, etc., right? Because it starts at 0th order, right? This one, on the other hand, has what? This starts with, it has x squared, x cubed, and so forth type terms, right? It starts at order 2. The other one starts at order 0. So, you know, which of these does not belong? I mean, for this reason, the 0th and first order terms on the left sum are special, right? They're not part of the general story. We should separate them out and erase this. So what I would do, I would say, okay, so n equals 2 gives me what? 2, a2. N equals 3 gives me what? 3 times 2, which is 6, a3x, right? Those are the first two terms in here. And then I have plus the sum n equals 4. This is n equals 2, this is n equals 3. So n equals 4 to infinity of n times n minus 1, a sub n, x to the n minus 2. And then I still have plus the sum n equals 0 to infinity of a sub n, x to the n plus 2. Now at least both of these sums are starting at the same order. They're still indexed differently, but they both start at order 2, right? N equals 4 gives me an x squared, and n equals 0 gives me an x squared on the other one. So what I usually do at this point is I make a substitution. And for this one, I mean, you could make them, you could convert one to the other, but I'll just convert them both to something that's different. So I'm going to let n minus 2 equal to j. And over here, I'm going to let n plus 2 equals to j. These are separate substitutions. This would be akin to maybe you're doing an integration, right? And you got like dx over x minus 2 plus the integral of dx over, of x dx over x squared plus 2. Here you'd let u equal x minus 2. Over here you'd let u equals to x squared plus 2. These are separate u's, and yet I use u for both. This doesn't usually trouble calculus students, and yet for some reason, when I use j for two separate things here in two separate substitutions, something happens. So I'm trying to remind you, this is just notation to illustrate a mathematical idea. Anyway, so with this substitution, these guys are still out front, minding their business. We get the sum. Now what happens? N equals 4, j equals what? Well, n equals j plus 2, right? For the first one. Over here, n equals to j minus 2, right? So for this sum, n equals j plus 2. So we get j plus 2 times j plus 1, a sub j plus 2, right? J equals what? J equals, n equals 4, j equals what? 2. Yeah. And that's all to the x to the power j, plus the sum. Again, j equals 2 to infinity, a sub j minus 2, x to the power j. These are different substitutions, just like I might use u in two different ways in calculus 2 earlier, right? Or calculus 1. These are both summations, right? So the summation variable, the so-called dummy index of summation, you could change j to whatever you want. It wouldn't change what this is. It's just a label to express the summation. Now the reason I want them to look the same is so that you can clearly see that they're both the same format, so we can add them. So we get 2a2 plus 6a3x plus the sum, j equals 2 to infinity, of j plus 2 times j plus 1, a sub j plus 2, plus a sub j minus 2, all times x to the power j. And that's all equal to 0. Okay? Any questions so far? The reason I've done this is because I need to get the expression to a series where I can clearly see order by order everything, right? And so at this stage in the game, I can look at, let's call this thing star. I can look at star and I can see a couple things easily from star. Okay, so from star, we read from constants. The constants are what? I got 2a2 equal to 0. From the x terms, I've got what? 6a3 equals to 0, right? So therefore, a2 is 0. a3 is 0. That's good. Okay. And what else do I get? For j greater than or equal to 2, we have that j plus 2 times j plus 1 times a sub j plus 2 plus a sub j minus 2 is equal to 0. This means that there's a link between the coefficient minus 2 and the coefficient plus 2. Now, I personally don't like that formula. So what I'm going to do is, first of all, I don't like j. My j is ugly, so I like n better, just personal reasons. But I'm going to change this formula into something that's a little bit easier for me to kind of get my paws on. And so I'm going to let n equal to j plus 2. If I do that, then I can make this formula nicer. Since we're going to do some work with it, it's in our vested interest to make this nicer. So that's n times n minus 1 a sub n plus a sub n minus 4 equals to 0. And that's going to be for n what? N greater than or equal to what? If j is greater than or equal to 2, and n is equal to j plus 2, n is greater than or equal to 4. And then finally, this is the final form for further investigation. A sub n is equal to minus a sub n minus 4 divided by n times n minus 1. Let me call this star star, because that's what we want to focus our attention on here. Right? That says there's kind of like a fourplicity to the solution. There's some sort of linking between, things that are related by a shift of 4 or a multiple of 4. I know some math might be helpful here. You can look at the integers as being partitioned into things, right? The integers, you've got 4z plus 1, 4z plus 2, 4z plus 3. So any integer, if you pick n in z, you can either have n is equal to 4k, it's equal to 4k plus 1, it's equal to 4k plus 2, or it's equal to 4k plus 3. Any integer can be written as one of those 4 classes, right? That's the possible breakdown of an integer if you look at in terms of 4s. We usually do this with even and odd, right? Numbers are either even or odd. You're used to that. But you could also do this. This is a further refinement. Yep. Integers. So if you like, you could write it this way: 0 plus or minus 1 plus or minus 2 plus or minus 3. So either adding fingers or taking them away, I guess. But I take away so many, I don't know. What would mean minus 11 fingers? You'd have to be a mutant to start with, Or maybe you've just grafted someone else's hand onto your body. Then you can have minus 15, right? What's that? Why would you do that? I don't know. So you could illustrate minus 15. We're talking about where numbers are from. I don't know. You asked me what z was. This is all your fault. Let's see here. Integers. So, yeah. My point, getting back to the point here, from star star, if we look at star star, right, a sub 2 equals to 0, and a sub 3 equals to 0, that implies that a sub 4k plus 2 is 0, and this implies that a sub 4k plus 3 is equal to 0. Well, for k equals to 0, 1, 2, and so forth. See, the fact that a sub 2 is 0 forces a sub 6, and a sub 10, and a sub 14, and a sub 18, and all the way on up to be 0. If I add any multiple of 4 to a sub 2, this forces them to be 0, because a sub 2 is 0, right? It's like a sub 6 will be 0. A sub 6 plus 4, a sub 10 will be 0. A sub 14 is 0. Likewise, for 3, 3 is linked to 7, which is linked to 11, which is linked to 11 plus 1, 4 rather, 15, which is linked to 9. You get the idea. So anything of the form 4k plus 3 will be 0, because these are 0, right? But on the other hand, we get no particular restriction. Things related to a sub 0 and a sub 1 survive. Right? Because those are not forced to be 0 by the initial conditions here, so to speak. In particular, we can look at a sub 4 is equal to minus a sub naught over what? 4 times 3. A sub 8 is what? A sub 8 by star star is minus a sub 4 over 8 times 7, right? But then that's equal to minus a sub naught over 8 times 7 times 4 times 3, right? A sub 12 is minus a sub 8 over 12 times 11, which is minus a sub naught over 12 times 11 times 8 times 7 times 4 times 3. Right? And this pattern continues. On the flip side, we have a sub 5 is minus a sub 1 over 5 times 4. A sub 9 is minus a sub 5 over 9 times 8, which is, by the way, a sub 1 over 9 times 8 times 5 times 4. And a sub, let's say 9 plus 4, 13, is minus a sub 9 over 13 times 12, which is going to work out to minus a sub 1 over 13 times 12 times 9 times 8 times 5 times 4. And so I can write the answer. Hence, y is equal to a sub naught times the sum. Let's see here. K equals 0 to infinity. And what is the pattern of the coefficient? Let's see here. I got to think about this for a second. This is a sub 2 times 4, right? This is a sub 3 times 4. What's my pattern? Okay. So it is minus 1 to something. What's the something? I'll do the easier part. Downstairs, we've definitely got 4k, right? We've got 4k times 4k minus 1 times, you know, in principle, 8 times 7 times 4 times 3, x to the power 4k, minus 1 to the what? Let's see. When we have k equals to 1, we get a minus. When we have k equals to 2, we get a plus. When we have k equals to 3, we get a minus 1 to the k, right? Yeah, you're fine. It's just easier to, if you're writing, you have ownership of it. You know, these are my thoughts. You're just trying to hear them after me. I always have trouble following people's work. Yeah, so those are the attached to a sub naught. Then the a sub 1, sum k equals 0 to infinity. We have 4k plus 1 times 4k Eventually we get to 9 times 8 times 5 times 4. All right, and that's x to the power 4k plus 1. And I need my sign. Looks like it's minus 1 to the k again, right? There you go. So you should be proud of me. I usually have this bad habit in here of working examples of decreasing difficulty. I start out with the most difficult example possible, and then I decrease the difficulty from there. Today, I have actually done the pedagogically sound practice of giving you the easiest examples at the start and working our way to this example. Yes. Oh. Wow. Is that all I need to do? I guess if I ended class now, then this would be like the ultimate class. And yet I won't. Let's see here. Sorry, I tease you like that. It's like you jerk. Anyway, this is this is pretty much it for power series at what's called an ordinary point. So power series at an ordinary point, they can be solved by just plugging in a power series and working out these recurrence relations, all right? And it will always be the case for these kinds of problems that the solution exists and can be found and so forth. But we've already worked some examples which are not like this. Cautionary tale. How about this one? X squared y prime prime plus 3x y prime plus y equals to 0. Let me just tinker with this for just a second. Let me just make that an x, and let me make this a minus, I don't know, fourth. So you remember how this went? We did r times r minus 1 plus r minus 1/4. We got r squared. We got r squared minus 1/4, which gave us r plus a half times r minus a half, right? And our solution was y is equal to c1 x to the 1/2, well, x to the minus 1/2 plus c2 x to the minus 1/2, x to the 1/2 rather. Shut up. X to the 1/2. And I actually needed to say, hey, x is greater than 0, otherwise, So this is apparently an example which is not going to work out for us with the power series technique, right? I mean, look at the solution. The solution we know from other methods. This is the Cauchy-Euler problem, right? Cauchy-Euler problem, which kind of looks a lot like, not so different. We just solved y prime prime plus x squared y equals to 0, right? Which I'm made of. That might be a homework problem of yours. If it is, I'm sorry. My apologies. Maybe there's at least like a minus here, or a 2 or something. All right, I don't know, but hopefully it's a little bit different. This is a lot like this, right? But these are very different problems, because the latter problem. Shut up. See here. The latter problem has this as solutions, right? I mean, this is another notation that might be more familiar. C1 over root x, right? Plus C2 square root of x. What are the domain of power series are what? They're open intervals. What's the domain of this thing? The natural domain of the solution here is 0 to infinity. That's not the domain for a power series, right? This is something else. So this does not fit into this general umbrella of what we've been doing today. So what is this, You have a question?